Up until this point in this class, in chapters 1, 2, and 3, we've been studying mostly just mechanics, so motion. Now we're going to start studying dynamics, which is looking at the cause of motion, which is forces. This whole chapter will focus on Newton's laws, but this particular video will just discuss the forces. The first force that we're going to talk about is gravity. Gravity is the weakest of the forces and is very small unless objects are very large. What that means is that unless the object that is exerting this gravitational pull or this gravitational force, unless that object is very large, the gravity of that object will be small. Now this seems kind of strange because we can feel gravity of the Earth all the time. But we have to remember that the Earth is very large, and therefore the gravitational force that the Earth can exert will also be very large. Gravity is also a long-range force, meaning that it can exert itself over a long distance. You can remember this by thinking about the idea that if we drop something from very high up in the sky, that object will fall down to Earth, even though the object begins at a very far distance from the surface of the Earth. The next force is called electromagnetism, or electromagnetic force. This is also a very long-range force, and this is the force that's responsible for binding electrons to nuclei. This is due to the attraction as well as the repulsion of different components of the atom that allow this electromagnetic force to occur. A third force is called strong force. This is the strongest of all the forces and holds protons and neutrons together in a nucleus. If you consider that like charges will repel one another, if we have multiple protons which have the same charge within a nucleus, then those protons should be repelling one another constantly. So with this force, this allows the protons and the neutrons to remain within the nucleus of the atom. Now, while this is a very strong force, it's also a very short-range force, meaning that it only has to exert its power over a very short distance within the atom. The last force is weak force. This also has very short range, and we see this force when we look at radioactive decay. Although it is called weak force, remember that gravity is still considered the weakest of the forces. Now we're going to get into looking at how to calculate or measure force and net force. Before we begin the idea of looking at force and net force, I do want to readdress the idea of a net change. So let's think of a net value that we might know already in our lives. So let's take an example of Stella's wallet. Say on October 1st, she starts with $16. On the 13th, she babysits, gets $10, and now she has a total of $26 in her wallet. She went to the movies a week later, and it cost her $7, now with a total of $19 in her wallet. On the 25th, she found $3 on the road, and now she has a total of $21. And on the very last day of the month, she bought ice cream for her friends, which cost her $10 for a total of $11. If I were to ask you what the net change in Stella's wallet was, you would probably already know how to calculate this. You would take the final amount of money that she had and subtract the initial amount of money that she had. So she would have a net change of -$5. Now, in order to figure this out, we had to consider all of the changes that occurred throughout the month. However, we can sum up all of those changes with a single value. And that's what we'll be doing with net force. We will take all of the forces acting on an object and determine what the overall change in that object's motion will be. So let's talk about force. Force is simply something that is capable of changing an object's state of motion. Now remember this idea of being capable. In other words, it has the potential to change an object's state of motion. This does not mean that it has to change an object's state of motion. Think about what would happen if you pushed against a wall. You're clearly presenting a force or exerting a force on that wall. However, the wall will not move. If you keep that example in mind, this will remind you that a force does not necessarily have to change the state of motion of an object, but rather is simply capable of doing so. A change in motion is called acceleration, and this idea of force is a vector. This makes sense. If we have acceleration, which is a vector, and we are causing a change in that vector, we can do that with another vector. When we say that force is a vector, remember that that means that it has to have two things, magnitude and direction. Remember that it makes a difference whether I am pushing on an object in one direction or pushing on that same object in a different direction. Now there's a couple different types of ways that forces can be applied. We have contact forces, which are either pushing or pulling an object by touching it. And we have added distance forces, which we've already talked about. Things like gravity, magnetism, and electrical forces. We can create diagrams to show what these forces are doing to a certain object in order to calculate net force. Now remember that net force is the sum of all forces acting on that particular object. That means that this net force is representing a resultant. The way that we can draw diagrams to represent net force is by doing what's called a free body diagram. These diagrams are exactly the same as any other vector diagram that we've shown, but now in the middle we will show a box or a dot. That box or dot is simply to represent the object itself. In order to draw these diagrams, there's a few things that we need to remember. The first is to identify all forces acting on the object. The second is to make sure that we are only using forces acting on the object. In other words, we should not include forces that the object is exerting on something else. Third, we need to make sure that we draw a vector to represent each force. So we're drawing an arrow to represent each force. These arrows should always point away from the object. So think of the object as being in the center and each of the arrows as pointing out from that object. And finally, you want to make sure to label each force. In other words, you're demonstrating what is causing each force or what is exerting each force on the object. Let's look at a couple examples. So here we have a free body diagram with only one force acting on the object. In this diagram, we have one force pulling to the right, which is a positive direction. Remember, think about the XY axis. So if we go to the right, that would be the positive x-axis. So here, since we have no other forces to sum with this positive right axis force, we can call the force, or the net force rather, 10 newtons. Here we have two forces acting on the object. One force, 4 newtons, in the positive direction, and one force, 10 newtons, in a negative direction. To find our net force, all we need to do is sum these two vectors. So we have positive 4 newtons plus a negative 10 newtons, which equals negative 6 newtons. In other words, the total net force is for this object to be pushed 6 newtons in the negative direction. Here we have an object being pushed or pulled with 10 newtons to the right in a positive direction and 4 newtons to the left in a negative direction. So we sum these two together, positive 10 plus negative 4, and we get 6 newtons, positive 6 newtons. In other words, this object will be pushed or pulled with a force of 6 newtons to the right in a positive direction. Here we have a free body diagram with 4 forces acting on the object. Whenever we look at these types of diagrams, try to figure out the overall net force in one direction and the overall net force in the other direction. So here, our change in the x direction is that we have a force of 5 newtons this way to the right and 5 newtons this way to the left. We sum those two vectors, 5 newtons plus a negative 5 newtons, to get a 0 Newton force going left to right. When we look at the forces being applied up and down, this is our change in y. We have 5 newtons going up in a positive direction and a 2 Newton force going down in a negative direction. This results in an overall force of 3 newtons upward.